Hello, this is the Chapter 1 summary video. In this video, we'll talk about an introduction to matter, energy, and measurement. We'll also discuss significant figures. Matter, of course, is anything that has mass and takes up space. Some examples of matter include atoms, molecules of a compound, and mixtures. These aren't all the examples of matter, these are just some examples of matter. Now, some elements exist as atoms at room temperature. Examples of these would be things like the noble gases, so things like helium, neon, argon, etc. These are examples of elements that exist as a single atom at room temperature in their standard state. Other other elements more commonly exist as a molecule at room temperature and atmospheric pressure. Examples of these would be things like hydrogen gas, nitrogen gas, oxygen gas, etc. Other examples of matter include molecules of a compound. Now, a compound is any type of substance that has two or more elements present. So some examples of compounds could be things like H2O, NH3, etc. Maybe something like NaCl. Now, water and ammonia, H2O and NH3, a little bit different from something like NaCl. NaCl being an ionic compound. We'll talk a little bit about those in Chapter 2. But ionic compounds will exist as a network of plus and minus ions that are all attracted by electrostatic forces of attraction. Whereas if you have a water sample, be it a solid, liquid, or a gas, you'd have a lot of individual water molecules that, if you're in the gas phase, really aren't interacting much at all. And then if the substance is in the liquid or the solid phase, then you have adjacent water molecules attracted to each other by intermolecular forces, but you still have intact and separate molecules. Same thing with something like NH3. In general, you have molecules or molecular compounds form among non-metallic elements when they pair up together. And then whenever you have a metal and a non-metal paired together, that's going to tend to go into the form of compound like ionic compounds. The key is that NaCl really doesn't form that molecule unit like H2O or NH3. So it's not like a salt sample is a collection of a bunch of NaCl units, but really just a bunch of collection of plus and minus ions that are all electrostatically attracted to each other. So you have all of these ions that are each electrostatically attracted to each other. And of course you can have a mixture, and a mixture can be anything you can imagine, from gaseous mixtures, liquid mixtures, solid mixtures. Maybe you have a solid mixed with a liquid. You can have heterogeneous or homogeneous mixtures. We'll define and talk about those a little bit later in this video. So, of course, we have a discussion early on of the different states of matter. I think what's really important for us to recognize is that most substances can undergo a transition from the solid to the liquid to the gaseous state. Water, of course, is special. So we have words for the solid, liquid, and gas state of ice, water, and water vapor. But the idea here is you go from having a collection of molecules that are not interacting much at all in the gas phase. So the gas phase, you have the molecules that are sort of separated, not really interacting with each other. As soon as the molecules start to see the interactions of the other molecules, that's when you're getting close to the condensation point. So you can condense the liquid vapor into the liquid phase. If you cool the water vapor, then you have water molecules tumbling around each other, but experiencing some intermolecular forces of attraction, kind of keep going, then eventually you get to the solid phase. The key here is that if you have a water molecule or a set of water molecules undergoing this transition of, say, melting to the liquid phase, that you still have intact water molecules, like the bonds between hydrogen, oxygen. Hydrogen, we'll see that these are called covalent bonds. These bonds remained intact through the solid, liquid, and gas transition. So you can have water liquid turn into water gas if you heat up the mixture. That these transitions are not breaking the bonds between the H and the O atoms within a single water molecule. Rather, they're just breaking the electrostatic attractions between two adjacent water molecules. So you're just undergoing the transitions of water being electrostatically attracted to, or intermolecularly attracted together, to not as much in the liquid phase, and then completely separated in terms of the gas phase. So I think it's important for us to, at this stage, recognize the difference between intermolecular forces, such as those that might unite molecules together in the solid or liquid phase, and then the absence of those forces in the gaseous state, but that we're still keeping those covalent bonds intact. So we can classify matter based on its composition. So we might want to look at matter and try to determine whether it's uniform throughout. This is usually best done just by inspecting the matter if you can. If you can see two different phases, then you clearly have a heterogeneous mixture. So if you can clearly see two liquids have separated in terms of, an oil and water layer, and maybe you don't know which layer is the water, which one's the oil, but you can clearly see two layers and you have a heterogeneous mixture. So you can usually look at matter and then try to assess whether it's uniform throughout. Like if you had an intact orange, clearly that is a heterogeneous mixture because some part is the peel, some part is the fruit, and clearly there's two different sort of layers or separate pieces. So definitely an intact orange would not be uniform throughout. Now if you had a glass of orange juice, like you're just looking at the actual juice part and not the glass, obviously the glass and the orange juice together would be some sort of a mixture. But if you're just looking at the orange juice itself, probably looks pretty homogeneous. So it looks like a single phase, maybe like a glass of milk as well would look homogeneous. Milk generally has that word homogenized right on the label. So homogeneous just means that it's uniform throughout. Then another question we might ask is, does it have a variable composition? Now this usually is not something you're going to answer just by looking. Like if you had like a clear liquid, you would really be none the wiser if that was pure water. And maybe it's water mixed with alcohol. Maybe it's brine, which is salt water dissolved into, brine would be salt dissolved into water. So if you just had a clear solution and you're just looking at it, you really couldn't tell with the naked eye all the time if that was necessarily of a variable composition. But the variable composition part is really just saying, if you could look, say, with a microscope or have molecular goggles, not really a thing, but if you can imagine looking at the different molecules, would some of them be different than the others? It's really just a fancy way of saying, is there more than one thing there? Is there more than one substance present? If so, then we have a homogeneous mixture, in which we have two or more different substances present together. We could have a salt dissolved in water. We could have a tremendous number of examples. And then you can also then say, well, if it doesn't have a variable composition, then it must be some sort of a pure substance. So if you're looking at all the molecules and they're all water molecules, then you have pure water. And then if you're considering water, then water obviously contains two different elements, and so that would be a compound. And so then if you're analyzing and again, you can't know that just by looking, so you'd have to know something about the sample. Like let's say we're looking at a sample trying to analyze graphite. So we have graphite. Maybe you took the graphite from a pencil, removed the rest of the pencil, and you're looking at what's left. Turns out that that's actually carbon in its most standard state solid, graphite. So if you're inspecting carbon graphite, you maybe do a test, find that it does not have a variable composition, so it's a pure substance. Then that substance turns out just to be a pure element of carbon. So the pure substance, you can't really, it's kind of hard to assess that just by looking at the substance. Same thing with the variable composition, but usually if the matter is uniform or not throughout, that's something you can assess just by looking. So we have to have some sort of chemical knowledge about the variable composition and whether or not it's a pure element or a pure compound. So then we can classify matter or sort of visualize matter a few different ways. So atoms, of course, are the building blocks of matter. Each element is made up of a unique kind of atom, but can be made up of more than one kind of that atom. So that's really getting at isotopes. So this is getting at the whole notion that if you're considering something like carbon, and we'll see this in chapter 2 in a little bit more detail, but it has 6 protons and 6 neutrons in its most stable, or really most abundant nucleus. And then the next most abundant nucleus still has 6 protons, but actually has 7 neutrons. And so that's carbon-13 versus carbon-12. And that's relating to the mass number. We'll discuss and define those particular terms when we get to chapter 2. But the key being that, oops, I didn't write this right, 6 protons and 7 neutrons. So the protons, the number of protons in the nucleus is actually defining the atom. If you were to have, say, 1 fewer proton or 1 more proton, then that would be the element before carbon, which is boron, or the element after carbon, which is nitrogen. So if you had an atom with 7 protons, and that just happens to be nitrogen. How many neutrons it has, you'd have to know something. You can't just predict the neutron count. So say you know it's nitrogen 14, then you would know it's 7 neutrons. And again, we'll get into that sort of I'm somewhat regretting bringing this up, but I'm going to leave this in here for now, but that the 7 protons plus the 7 neutrons just add up to that mass number that we write for nitrogen. So if you know it's nitrogen 14, then you know it's 7 neutrons within that particular nucleus of that atom. But the key being, some atoms will have more than one type of atom that element can exist under ordinary conditions. So like carbon is about 99%, it turns out carbon 12, and about 1% of carbon turns out to be carbon 13. Now that's set by a lot of different factors that go well beyond the scope of this particular discussion here. But so most atoms do exist as more than one different type of atom in their standard state. And so then when we're picturing oxygen atoms, we're picturing 2 oxygens together for O2, H2O, 2 hydrogens onto 1 oxygen, CO2 for carbon dioxide. We'll get into naming compounds, the ones we're responsible for, when we get to the end of chapter 2. So a compound is made of 2 or more different elements together. And so then, of course, we can have much bigger molecules. We can have macromolecules, so things like aspirin. You could imagine things like DNA or proteins or things like glucose molecules. So there's lots of different types of molecules that go much beyond the complexity of this introductory chemistry class at this point. So compounds have what we call a definite composition. So this is the law of constant composition, or the law of definite proportions. This just means that a water molecule is always made up of 2 hydrogens and 1 oxygen. And not 3 hydrogens and 1 oxygen ever, but always 2 hydrogens for every 1 oxygen. So that's a law of either constant composition or definite proportions. And so then you can imagine also that if you take water and you convert it into O2 into H2, that you're going to get only half as much O2 as you do H2. And that's just sort of balancing out that chemical reaction. So if you're taking H2O over to the products of H2 and O2, then we're going to have to take, on average, for every 2 water molecules, we're going to get 2 H2s, but only 1 O2 to keep our reaction in balance. That's actually the law of mass balance. We'll talk about that a little bit more when we get to chapter 2. But we're not creating or destroying atoms. We're just undergoing a change on the left side into the new products on the right side. But we'll talk more about reactions later in the chapters. Actually, I think that's in chapter 3 that we start talking about chemical reactions. So let's talk about some different type of properties. 2 terms here. Intensive properties are independent of the amount of substance that is present, and extensive properties depend upon the amount of substance present. Now there's a key here. So the intensive properties are independent of the amount of substance. They are key to identifying the substance. So they are characteristic properties of the substance, not of the amount of the substance that you actually happen to have present. So an intensive property, this is just something that's a characteristic property of that substance. So things like densities, boiling points, colors, melting points, these help us identify substances. An extensive property, one that does not depend, an extensive property that does depend on the amount of substance present, really just relates to how much of the substance you have. So like mass, volume, energy, those are just properties that relate to how much of the substance you actually have present. So they're just not really telling you anything about the substance itself, but just how much of it you happen to have. Now, one thing that's kind of interesting is you think of density as the ratio of mass to volume. So mass, just, the mass of a substance, that's an extensive property. Volume, that again just relates to how much you have. That's an extensive property. But the mass to volume ratio for a substance, now this is an intensive property. So the density is a characteristic property. So substances just have their own densities. Now, there's some rhyme and reason behind why their densities are what they are, but that goes well beyond the scope of where we're at in the class right now. So substances just have a characteristic density that's relating to how much mass to volume there would be in terms of a ratio. So the ratio is an intensive property, but the specific mass or volume of the substance you happen to have present is just, again, an extensive property. So we can talk about different types of changes. So a physical change is a change in matter that does not change the composition of the substance. So examples are change of state, temperature, and volume. So if we go from having a little to a lot of water, we're not breaking or changing the bonds between water molecules, so that's not a chemical change, that's just a physical change. And those phase changes, so water solid converting to water liquid, converting to water gas. These are all examples of physical changes. So a change in physical state is just a change in the physical nature of the substance. You're not making and breaking new bonds among the atoms in the substance. As soon as we start breaking bonds, imagine we take CH4, pretty common reaction. We do this all the time, burn it in the presence of oxygen to make CO2 and water vapor. One of the things that's, I'm sure you all have seen in a house that has a natural gas stove. If you're like cooking spaghetti, say on a cold day, you have a pot of water in the stove. So you're vaporizing the water and you're also creating water from the natural gas that you're burning. You're going to see water vapor sort of condensing on your windows. So you've probably seen that if you happen to have a gas stove. But so methane plus oxygen, this is not balanced. So if we want to balance our reaction, we'd have to make like 2 water molecules. Then we have 2 and then 4 oxygen, so we need 2 O2 molecules. So we have methane gas, oxygen gas, creating CO2 gas, and water vapor here coming off of this reaction as this reaction is taking place with heat. So it's a reaction taking place with the flame. So this is our first example of a combustion reaction. We'll talk more about those in chapter 3. But the key here is that we're changing the nature of our substances. So we're making new covalent bonds from breaking our sort of reactant covalent bonds. We're breaking the bonds in CH4 and in O2 and then making these new bonds in our products. We'll talk all about that as we go on throughout the class. So we can separate mixtures using different techniques. Our main techniques are things like filtration. This is good to separate a solid from a liquid. So if you have a solid and liquid together, just grab some filter paper and separate using like a funnel. You can also distill. This is helpful when you have like 2 liquids that are needed to be separated, such as say water and ethanol. So you can actually only ferment alcohol to probably about 15 to 20% or so alcohol percent by volume. So if you want to increase that and have more of a spirit, then you would want to heat up the mixture and then collect the vapors. The vapors are going to be more concentrated in the lower volume ethanol. So ethanol has a boiling point of about 78 degrees C. Water, of course, has a boiling point of 100 degrees C. So you can separate substances by difference of boiling point using distillation. I think there might be a picture coming up in a moment. If not, there's a picture in the textbook. Chromatography is that sort of example. You have like an ink blot, maybe on a sheet of paper. It gets wet, and then as it gets wet, you sort of start to see these different colors emerge. And so the different colors that you see, usually blue and violet are the colors that you'd see emerging from the ink blot. But the reason why you might see these colors emerging is because the black ink is actually a combination of different sort of colored dyes. There's really no black dye in the ink pen. There's really just a combination of different colors to make that color appear black. And then when you have water run through the mixture, if water then runs through the mixture, it turns out that the ink dyes of the different colors have a different like stick rate, if you will, with the paper. So their affinity for paper is different, so then you can see those colors emerging and separating from each other. Now this is really useful, more useful maybe in organic chemistry than general chemistry as an actual technique. What you can do is have something called like silica gel. You can add a compound onto that if it's a mixture, and then you can separate by allowing a solvent to run up through the plate through something called thin layer chromatography. So you'll probably discuss that and then do experiments with that when you get to OChem, if you happen to take the 25, 10, 20, and then 40 and 50 labs. Okay, and here's some pictures to show the examples. Of course, filter paper and a funnel are all you need to separate a solid from a liquid, so that's pretty easy. Here's an example of a distillation. So you have the example that we're using here is just salt water. So the sodium chloride in the salt actually has the lower vapor, or the lower boiling point. The boiling point of salt's really high. So if we distill the mixture, we're going to have the water vapor in the vapor form, and then we can condense those vapors and then have a more pure water sample once we distill the mixture. And so you may actually need to distill this more than once, and that's kind of sometimes a problem in distillations, is how many times you actually have to carry this distillation out in order to get the purity that you're looking for. But so you can separate substances. So the salt has a boiling point that's very high. Whoops, that's not boiling point. So it has a boiling point that's very high. and then water's boiling point is relatively low, comparatively speaking. So we can separate by basis of heating up the mixture, collecting the vapors in a different container. Now, chromatography, here's an example. This is more what you'll do in organic chemistry. But the technique here is you fill up a what you call a stationary phase with something like silica gel, something that's kind of like paper, something that's just a solid that the compound that you want to add to it, or the mixture you want to add, has different components that just stick to that substance at different rates. So then as you allow that substance to go down the column, you get a separation of the components of that mixture. Kind of just like you imagine the ink blot separating with water running through your ink dye. And so this technique here is called column chromatography. And you'll learn more about that again in OChem. So let's discuss a bit about energy. So energy is the capacity to do work or transfer heat. So it's the energy that you have to put objects into motion, or to heat objects up. So if you have energy to give, you can put something into motion or you can heat something up. So work is the energy transferred when a force is exerted on an object, causing a displacement of that object. So work, I like to call, is like the energy associated with motion or putting objects into motion. Heat is the energy used to cause the temperature change of a substance, usually thinking of giving a substance energy, so its heat can increase or its temperature can increase. And then a force is any push or pull on an object. Now, where this comes into chemistry has a little bit to do with potential energy. So kind of differentiating what we think of kinetic and potential energy is maybe worthwhile to differentiate the two forms of energy. I think we're used to thinking of the more obvious physics examples of having a bicyclist at the top of the hill has a lot of potential energy, and that energy can be transferred into kinetic energy into the bicycle as the bicyclist loses their potential energy going down the hill and eventually getting to the bottom of the hill and then stopping. So potential energy is sort of related to the position compared to other objects. If you're higher up, you have a greater potential energy than if you're lower down. Kinetic energy, meanwhile, is just the energy associated with motion. So kinetic energy is just equal to 1/2 mv squared, where v is the velocity, m is the mass of the object. So if an object's in motion, then it has a particular kinetic energy that's associated with the mass and the velocity of that motion. And so in the physics example, you can sort of transfer the two energies to and from each other. You can take potential energy if you're high up on the hill. Again, push yourself down the hill, you go faster, you pick up kinetic energy as you're losing that potential energy. Okay, now where this comes into play in a chemistry class kind of has to do with the potential energy and the kinetic energy you might imagine that might accompany, say, a chemical reaction. So imagine H2 and O2. I'm going to just switch colors here. Let me go to more black. Okay, so imagine we have H2 and O2. We mentioned the reaction of water forming H2 and O2 earlier, but let's imagine the opposite reaction, H2 and O2 getting together. It turns out that H2 and O2 are kind of like the bicyclist at the top of the hill, and water is actually the bicyclist at the bottom of the hill. So our two H2O molecules are at the bottom here, and that's because water turns out to be more stable. The bonds are stronger in water than they are in H2 and O2. So we kind of have like some stored energy in H2 and O2 if we have those as our reactants and present, say in a balloon that maybe we can put a match to or a spark to, and then quickly have a reaction that takes place where the bonds start breaking in the H2 and the O2, and then we start forming the products water. So water just turns out to be more stable. You can sort of prove that to yourself a lot of different ways. One is just knowing that you put H2 and O2 together and putting a flame to it and seeing that something happens. And then if you do the opposite, if you try to put a flame to water, it's not going to magically blow up and return back into H2 and O2. An interesting thing does turn out to be the case that just about any reaction can be powered in reverse. That is, if you just imagine finding a way to do this, but if you can somehow add electricity or a lot of energy to water, you can actually back turn that those substances back into H2 and O2. So you can electrolyze water. The electrolysis of water can lead back to H2 and O2. If you're looking at that as a source of H2, it's kind of like energy neutral. It's really not gonna be an energy source per se, but maybe a transfer of energy or maybe a way to store energy. People have talked about maybe storing sunlight by converting water into H2 so that then when the sun goes down, you can use H2 and O2 to be an energy source then to provide energy as you go back down the hill. But sort of the key is that to get up the hill, you got to put energy in. Get down the hill, you get energy out. And so that's where kinetic and potential energy come into play within a chemistry class, is that we're going to begin discussing, things like enthalpy in chapter 5, where we're going to try to follow the heat changes of a reaction so we can kind of see when different types of reactions occur, they can absorb heat or maybe give heat off depending on the nature of that particular reaction. So we'll take a look at heat changes of reactions and think about more pictures that relate to something like we've sketched out here for H2 and O2 and water when we get to chapter 5. Okay, so we have our first sort of sample pause and complete videos. Now, what I would kind of do here at this point, if you're willing to try some problems out, is just go ahead, hit pause, read through the questions, give them a try, and then, hit play and you can check your work. Okay, I hope you gave these problems a look at first here, but so the first one saying white gold contains gold in a white metal such as palladium. A sample of white gold is uniform throughout. Classify this as a element, compound, pure substance, mixture, and if so, what kind of mixture? Okay, so for this problem here, you might be fooled into thinking this is an element just because it's called white gold, but that's just its like trade name. So obviously it's a mixture because we know it has two different substances together, two different elements together, and so then it's some sort of mixture. And so the key is that we're told the sample is uniform throughout. Uniform throughout is the idea of it appearing to be homogeneous. So being uniform throughout means it's homogeneous. Knowing there's two things present make it a homogeneous mixture. Okay, so this substance would be a homogeneous mixture. Now, if it was not uniform throughout, then it would have been a heterogeneous mixture. Okay, and if that was the case, maybe we would have a picture of it, and you can kind of see with your eye that it looks like there's two different phases. So maybe you'd see, it would look like one color on one side and a different type of appearance on the other, and that would be heterogeneous. Okay, so let's classify grapefruit as an element, compound, pure substance, or a mixture, and if so, what kind? So obviously a grapefruit, thinking of the entire fruit, obviously has the peel and the rest. So this is a pretty clear example of a heterogeneous mixture. So that would be heterogeneous mixture, and obviously it has a lot of different substances like water, sugars, and materials within the actual grapefruit itself. So give an example of a substance found in a grapefruit. Probably the most abundant substance would be water. Maybe you'd have some glucose, C6H12O6. So those are a couple examples of substances you might find within a grapefruit. Okay, let's begin getting into units of measure. So we have a chart here showing the common SI units of length being the meter, mass kilogram, temperature is actually the Kelvin. The Kelvin temperature is the temperature in degrees C plus 273.15. So you may not have used this scale very often, but at 25 degrees C, room temperature would equal 298 Kelvin in the Kelvin scale. Time, the SI unit is, of course, a second. Amount of substance, the mole. We'll talk about that more in chapters 2 and 3. I think more in chapter 3. Electrical current and luminous intensity are not terms or types of units we tend to use in Chem 1210. You'll actually pick up a little bit with electrical current towards the end of Chem 1220, but that SI unit is the amp, and then candela for luminous intensity. So the key is that these are the only 7 base SI units. So any other unit that we might work with or encounter would be some kind of either derived SI unit or a non-SI unit. And so 2 quick examples of some units that you might consider to be derived SI units might be something like the cubic meter for volume, and then how 0.1 cubic meter is the definition of 1 liter. So like our liter for volume is our derived SI unit. And it does relate back to our SI unit of length of the meter. So there's a fundamental relationship for our derived unit of volume off of the base unit for length. And then also there is there's non-SI units are what I wanted to mention, so that you can have things like 2.54 centimeters equals 1 inch, where 1 inch is a non-SI unit. So you can have conversion factors that relate your SI units or our derived SI units over to some sort of non-SI system. Okay, so we have various prefixes that we can use to make units more or less useful to use or to write out. The common ones that we'll use maybe go from like giga on down to maybe about, I don't know, probably pico, or the more common ones that we'll use. But so a giga, 10 to the 9 watts would be a gigawatt, 10 to the 6 watts would be a megawatt, 10 to the 3 watts would be a kilo. So 3, 6, 9 for kilo, mega, and giga. And so then going smaller, deci, not one that we tend to use very often, but of course centi. You have the idea that 100 centimeters in a meter, 1,000 millimeters is 1 meter, and then etc. So you'd have 10 to the 6 micrometers in a meter. Now, if you look over here, you actually see kind of the opposite unit, if you will, and the sorry, oddly a typo. I don't know if this came from the textbook, so there must be an error in the textbook. But the centi is 10 to the minus 2, not 10 to the minus 1. But you can obviously divide all of these units on both sides by 100, and then classify 1 centimeter as 10 to the minus 2 meters, or the millimeter as 10 to the minus 3 meters. And so the chart here is using watts. So 1 milliwatts, 10 to the minus 3 watts. Of course, you could say 1 watt is 1,000 milliwatts. So there's always two ways you can give a conversion factor. You can say, well, how many centimeters are in a meter? And then you can also say, well, how many centimeters are in 1 meter? So how many meters in 1 centimeter, or how many centimeters in 1 meter? But what I would try to do is make sure that we know micro to the minus 6, nanos to the minus 9, picos to the minus 12. Make sure you at least have memorized the sort of prefix and then the quantity through about pico. And then continuing from there would be femto. We're not going to use that unit too often. Atto and zepto continuing. So volume, as mentioned earlier, is one of the more common units for which there's a derivation off of the SI unit of length. So of course, if you imagine a cube that's 1 meter by 1 meter by 1 meter, that would be a pretty large volume. So 1 cubic meter, as we mentioned earlier, was equal to 0.001 liters. And then the connection to centimeters, 1 cubic centimeter is equal to 1 milliliter, exactly. So that's an exact relationship. And then, of course, there's 1,000 milliliters in a liter. So connection between length and volume, connecting our base SI unit to our derived SI unit for volume. So we have different types of glassware that we use for different types of purposes. So we have generally glassware you can imagine that we're trying to deliver quantities with. So we have things like graduated cylinders, we have maybe a syringe, we have a burette. Now the difference between these devices might be the types of scenarios you use them in. A syringe is usually going to have a little bit more of a preciseness associated with it. So like if you need to deliver 5 milliliters, and it's okay if you deliver 4 or 6 milliliters, it's probably okay to use a graduated cylinder. If you need to deliver about 5.0 milliliters, but where you're kind of need to be careful that you don't deliver 5.1, or that you're delivering maybe between about 4.9 to 5.1 milliliters, then that's probably going to be doable with a syringe. So if you need to be a little bit more precise with the volume you're delivering, maybe you go with a syringe. If you want to deliver with even more preciseness, then you probably use a burette. You'll be using those in the lab in the first or second week of lab. So you'll get some experience with these. With the burette, you can be really careful and sort of nail down that volume to about plus or minus about 0.02 milliliters. So if you want to be really precise with the quantity of volume you're adding, you'll probably choose a burette to deliver the quantity of your liquid. A pipette works, and I should also say a burette would be useful to deliver even, say, 5.26 milliliters. So if you need to deliver a very accurate and precise quantity, you're going to find a burette and also the syringe to be pretty useful. The syringe is just probably going to not deliver that same amount of precision as the burette. Now, the pipette is something that has like a little bulb in it, and the bulb might be a 5 mil bulb or a 10 mil bulb, but the pipette has a marking on it that you fill up with your liquid, and then you have that meniscus resting right on that mark. And then when you deliver this, like you'll see, say like a 5, let's say you have a 10 mil pipette. That pipette is delivered or calibrated to deliver precisely about 10.00 milliliters, as long as you fill to that line very carefully and then take the last drip that might be hanging off the pipette, touch it to the side of your glassware, and then very carefully transfer it to the container you're moving that volume into. So this is the way that you can transfer a very precise and accurate amount of liquid. This works really well when you know you need to add, like, say, 10 or 25 milliliters of liquid very exactly to some sort of reaction vessel. A volumetric flask, I don't know if you use these very often in the general chemistry lab, but you might say have a 100 ml volumetric flask, and the flask just has a marking on it that if you fill the liquid to that marking, then you know you have about 100.0 milliliters. So you get maybe not quite as much precision. You don't get that hundredths place that you might get off a pipette or a burette, but you're going to get pretty good accuracy using a volumetric flask. Now this is a glassware that's designed to hold that particular volume. So this is a really, really good glassware. If you want to maybe put, maybe some solid in here, weigh that out on a balance so you get a really good mass of how much solid you're adding. And then maybe you're going to add water and mix that solid into it and then make a solution where you precisely know the particular volume of that solution. This device here isn't really good at delivering. So this device here would not actually be very good at delivering 100 milliliters to some other container because you're going to leave droplets inside the container. And it's not calibrated to deliver, it's calibrated to contain. So it's calibrated, and when you fill to the mark, it should be containing very, very close to that intended target. Okay, so let's talk about our temperature scales. We see our sort of key scales here being Kelvin. We mentioned earlier, you're just adding 273 onto your Celsius temperature. And we also have the conversions between Fahrenheit and Celsius. I kind of like to think about the 25 degrees C, our sort of usual room temperature in Celsius. If you multiply that by 9/5, and so that would be basically 9 times 5, so that would be 45 plus 32. That works out to be 77 degrees Fahrenheit. So I think it's just useful to know that 25 degrees C is about 77 degrees Fahrenheit, and then that would be 298 Kelvin. And of course, you don't use a degree symbol like you do with Celsius and Fahrenheit for the Kelvin scale. And then also we see the conversion. If you have a Fahrenheit temperature and you want to go to Celsius, you can sort of either just rearrange your equation or use the equation noted here. So the one thing I think that's worth noting is that if you think of 0 degrees C, you add 273, that's 273 Kelvin, that's pretty easy. So then if you have 100 degrees C, you add the 273, that gives you 373 Kelvin. So notice that this difference here is 100 Kelvin. Of course, this is a 100 degrees C increase in temperature to go from the freezing point to the boiling point of water. Now, if you are an international student, you may not know the Fahrenheit scale, but 32 degrees Fahrenheit is the freezing point in Fahrenheit, 212 is the boiling point in Fahrenheit. Obviously, that difference here is not 100 degrees. This is actually greater than 100 degrees. It's almost 200 degrees C increase in the Fahrenheit scale. So if you go up a degree in Celsius, you're probably going up more than a degree in Fahrenheit. And then if you're going up a degree in Celsius, then you're also going up 1 Kelvin. So like going from 25 to 26 degrees C is the same as going from 298 to 299 Kelvin. So a 1 degree increase in Celsius is the same as a 1 degree increase in the Kelvin scale, not necessarily true within the Fahrenheit scale. That comes into play when we get to chapter 5. It's something that sometimes is confusing when you get there, but it's just different scales, but it's the Celsius and the Kelvin scales are pretty synonymous with each other. The Fahrenheit scale kind of off on its own little, on its own scale. Let's talk about some different units associated with energy. So we mentioned earlier kinetic energy is 1/2 mv squared. Turns out that joule is our derived SI unit. If you think of the SI unit of mass, that's kilogram. Velocity would be a derived SI unit. That's a pretty easy one. The speed being the meter per second, SI unit of length and time. And then we're going to square that. And so then 1 joule turns out to be equal to 1 kilogram meter squared per second squared. We can rewrite that. So 1 kilogram meter squared per second squared. So that is the SI unit of the joule. And so then the non-SI unit that we tend to use a lot on food labels is calories. So the connection to thermodynamics would be 1 calorie is 4.184 joules. but that's not necessarily the nutritional calorie that you see on food labels. The food calorie is actually the kcal scale, and they actually use a capital C whenever they're designating that scale compared to the little c calorie. So little c calorie is equal to 4.184 joules. One capital C calorie is equal to 1,000 calories, and 1,000 calories would be equal to 4,184 joules. So if you're ever kind of comparing how much energy you get out of like a food sample and you're off by a factor of 1,000, it's probably you forgot to account for that the calories in the food label are actually listing kcals, not calories, or capital C calories, which again is representing the kcals. And if you get big into nutrition, you get into like nutrition forums, you often see people say, how many kcals do you consume today? Well, that would of course just be the number of calories that you consume, the capital C calories. So we mentioned earlier, density is a intensive property relating or to extensive properties of mass and volume of a substance. So kind of showing this here that air has a characteristic density, wood has a characteristic density, ethanol has a characteristic density, same thing with water. So different substances have different densities, and those densities are generally a property of that substance. It kind of depends on how close or far those molecules get together or interact with each other. Gold, like our solids, tend to have a pretty high density. Our non-metallic substances tend to have a relatively lower density. But you see here that different substances have different characteristic densities associated with them because those are their characteristic properties. So we encounter lots of numbers in science, and it's going to be important for us to think about how the different types of quantities that we work with impact the calculations that we do with those types of numbers. So let's first talk about exact quantities or exact numbers. These are things we can count very carefully. Like we know that there are 12 eggs in a dozen. So if I tell you I have 2 dozen eggs, you know I have 24 eggs. You're not like, oh, do you have 1 or 2 dozen? It's like, no, I have 2 dozen eggs, exactly 24 eggs. Now, if I say I measured the length of an object to be, say, 24 feet, now you may wonder, like, is that 24 feet? Could it be 25? Like, is it 24.0, 24.00 feet? You may wonder how precise I actually mean when I say, you know, like say I go to the lumber store and say, okay, I need a 24-foot post. They may kind of say, well, how close do you need that to be 24? If it's like 24 plus a little bit, is that okay? Well, what they're really getting at is the preciseness, or how precise a measurement actually is depends on the tool that you use to make that particular measurement. Most measurements fall in the category of being inexact. So whenever we talk about making some sort of measurement, then those numbers depend on how they were determined. And scientific instruments have different limitations and errors. So an example here would be, let's say a room is 125 inches wide. An object is 1.25 grams in mass. So this object here, it's not 1.250000 grams. That would be a different measurement. We don't have that preciseness to make that claim for the mass of the object. What we know it to be is 1.25 grams. And that means that there's about plus or minus 0.01 grams in the understanding and the measurement of that particular mass. Same thing, if you say a room is 125 inches, in this class, we're going to take that to mean is that the plus minus here is about 1 inch. Our plus minus is in that last inch. If we more carefully measured the room, we might say it's 125.0 inches, in which point the error or the tolerance here would be 0.1 inch. So 0.1 inch if we say 125.0. So then the real issue starts to be when we start doing calculations with measured and inexact numbers, we have to sort of worry about how this impreciseness leads, and carries into the results of our mathematical calculations. But we'll get into that as we go along through this discussion of what we'll call significant figures. So let's tail off for a second and talk a little bit about uncertainty in measurements. And let's first imagine you're trying to measure temperature using a thermometer with like an old school thermometer. And so we can see here that we can see the temperature. And so, but how exact can we read this temperature? Like the actual device doesn't have markings between 25 and 30, so we're kind of like interpolating. So what we might be thinking, is it 26, is it 27, is it 28, is it 29? And it looks to be close to 27. Okay, and so it looks like it's 27, and the plus minus there is probably like half a degree C. You're probably like, well, is it 26 and a half? Is it 27 and a half? Probably somewhere within that particular range. And if I said it's 27, plus or minus about 1 would probably be about right. We're somewhere between 26 and 28 in terms of our measurement if we say it's 27. And so if we want to get that next digit of precision, if we wanted to be able to say, is it 27.0, or is it 26.5, is it 27.5, what we need is probably to kind of go back to the drawing board and choose a new type of thermometer, maybe choose a thermometer that actually had the markings on it. So imagine you choose a thermometer that has these graduated markings, then you could see very clearly, if we have these markings and we know they're correct and we trust our device, then we could say, oh, in this case here, that does look like 27.0. And then our accuracy there would be probably about 0.1 degrees C. So depending on the tool that we're using, we can end up with a different measurement. Like we might end up with maybe 2 significant figures in terms of 27. Maybe we use a better thermometer, we come up with a reading of 3 significant figures. And so then usually what you're going to need is maybe a longer thermometer so you can spread out those markings. And so it might take a little bit more money to buy a more sophisticated thermometer, but you can make even more graduated increments to maybe get more and more decimal places. And then from there, maybe move into a digital thermometer to get even more preciseness with that particular reading. So I've used the words accuracy and precision. I think we need to talk about those a little bit more. I think we have a slide coming up on that. Okay, so here's a slide that I was hoping would be next. So accuracy versus precision. So whenever we say something's accurate, what we mean is it's sort of on the intended target. So if you're aiming at the bullseye and you're hitting the bullseye, then I would say that that's very accurate. You're hitting the target exactly where you want to hit the target. And so then if you're aiming at the bullseye, but you hit 3 darts in a row, but way off target, I would say that that's very good precision, it's just bad accuracy. So you're very precise with your throws, it's just not on the intended target. And sort of the key here, though, is that somehow we have to know that you're actually aiming at the bullseye, and if you're coming in here, then that's how I know that your accuracy is poor. It's, you're not just playing some other dart game where you're actually aiming there. If I know you're aiming somewhere else and all 3 are coming on some other target, at least I know your precision, your repeatability is very good. So precision is a measure of how closely individual measurements agree. Accuracy is how close they happen to be to the true value. Now, here's how this relates to the experiments that we do. The number of digits that you see on a number is relating to how precise you know the quantity. And then how well that actual tool is calibrated relates to the accuracy. Okay, so if you know you have a balance that's really well calibrated and you get a bunch of decimal places, then you know you're kind of getting both high precision and high accuracy. So precision tends to, the idea being repeatability. I also like to think of precision being the more digits you're going to see, then the more reliable or the more precise that particular value is. So I would say, you have a 100-gram object versus 100.00 grams, that this has a higher preciseness. And then they're both pretty much the same accuracy. They're both kind of representing the same average value, so the accuracy of these 2 values would be about the same. So accuracy, how close are you to the intended target or to the true value, and then the precision, how repeatable is the measurement, or how many digits are present in the quantity. So significant figures relates to the digits in a measurement that are meaningful. We call those significant figures. When rounding calculated numbers, we have to pay attention to these significant figures so we don't overstate the accuracy or even possibly understate the accuracy of our results. And we can give a bunch of examples here. And so let's kind of begin. I'm sure the next slide is going to go into the sig fig rules, but let's do a couple examples here where we have 0.012 grams versus 0.0102 grams versus 0.120 grams, and sort of identify how many significant digits there are in each of these values. So the significant figures here would be 2, here would be 3, and then here would be 4. And so in none of the cases do we count these trailing zeros. And then in all the cases we do count the ending 0 if there is one. And then we always would count some sort of like a sandwich 0 as being significant. So like all the digits in the quantity are significant once we have a digit in the number and all of those that come after. Now there are some caveats. Like if I said 12,500, 1,250, This value here, it's a little bit ambiguous whether that 0 is meaningful or not. And so what I would say is that this value here actually has 3 significant figures for sure. And then if we want to imply that there's more, then we need to either have more information or give the value in something like scientific notation. So if we use scientific notation on 1250, we'd go 1.25 times 10 to the 3 if we're intending to report the value with 3 sig figs. If we want to report that value with 4 sig figs, we just add a 0. If we want to report the value with 5 sig figs, just add another 0. So this would be 5 sig figs represented and the number 1,250. Now it turns out if you had 1, 2, 3, 4, 5 significant figures, you could just do that as well. So 1,250, 5 sig figs, you can add a decimal point. But if you needed to represent that number with 4 significant figures, then just do 1.250 times 10 to the 4 for that particular value. That would be expressing that quantity to 4 significant figures. Okay, now let's deal with the trailing zeros real quick and kind of note that if you go scientific notation on any of these quantities here, that you should match the number of significant figures. Let's just do the first one. So if we go 1.2 times 10 to the minus 2 would be representing that number of grams, but in scientific notation. And so within scientific notation, I think you can clearly agree that that's 2 significant figures represented, and there should be agreement between our significant figure count. That's why we're not counting our trailing zeros, because they're just controlling where we write that times 10 to the power. So that's really not relating to the preciseness of the value. It's just relating to where the sort of numbers begin in that particular quantity. It's just kind of just pointing to where that decimal place is relative to the significant digits in the number. Okay, now let's do just a very simple like thought example. Let's say we have some sort of object that's 25 feet, and we know that's where 2 significant digits are what we know that value. And then let's say we're going to add some sort of other object that's also known to be 25 feet to that, and kind of say, well, what's the total length here? So we're using some sort of units. I like to throw units onto these calculations, so we're picturing these as measured quantities that are these inexact numbers that relate to this inherent impreciseness, that these aren't kind of ordinary numbers. We're not just like changing mathematics or arithmetic or dealing with ordinary arithmetic, but we do our arithmetic here 50 feet. This is accurate out to that 0, meaning it's precise all the way out to the 1's placeholder. And we'll see a rule, or the addition rule, kind of define that more carefully. But we're going to have to define that as 5.0 times 10 to the 1 feet, so that we appropriately show our value has 2 significant figures. So if we just said it's 50 and maybe imply that's only 1 sig fig, then we might be understating the number of sig figs in the quantity when really there's 2 significant digits there. So one of the ideas might be, if you think of one of these values or both of these values being plus or minus about 1 foot, what would it mean if we were sort of off on one in one direction or the other? So if one object's 25 feet and the other happens to be 24, then we'd be at like 49 feet. And then if we're off in the other direction, it would be 51 feet. So like our kind of like swaying here is between 49 and then 51. And so that's kind of why we're seeing, well, 50, and then that last plus minus is coming in that 1's placeholder. So we're going to say, that both those digits and 50 are significant. And again, we'll define a rule for that more carefully in a moment. But imagine you multiply 25 feet together. So if we're multiplying these values, I should have wrote a plus sign here, but let's say we're multiplying now 25 feet by 25 feet. I think that same analogy, if you go 25 times 24, I'm just grabbing a calculator, 25 times 24 is 600. The multiplication itself comes out to 625. So if we're off somewhere between 600 and probably 650. 26 times 25 is 650. So you see, we're off here now, but in that second placeholder, not in the first placeholder. We're off in this tens placeholder is where we see the variability in the inherent uncertainty in 25 feet times 25 feet, considering this inherent impreciseness expressed in those quantities. So what that means is these values here are only actually good to 2 significant figures. So what we're going to see when we add and subtract, we got to look for placeholders, and we have to round to a particular placeholder. We'll talk more about that in a moment. We multiply and then divide. What we're going to do is count sig figs. So we're going to see 2 sig figs times 2 sig figs. Our result's actually only good to 2 significant figures. So we might call that 630 feet once we do some rounding. And we might, if we want to report that clearly, we might say 6.3 times 10 to the 2 feet. So again, we don't want to understate or overstate the preciseness of the results of a calculation due to this inherent impreciseness involved in these measured quantities. Okay, so here's those basic rules of sig figs again. So like the non-zero digits are always significant. Zeros between non-zero digits are significant. The zeros at the beginning of a digit are never significant, and then the zeros at the end after a decimal point are significant. Again, so another example would be 0.10050, 1, 2, 3, 4, 5 sig figs. And if we had 10,500, let's say, we got 1, 2, 3 sig figs. And there's some examples here. So this is using scientific notation, 1.03 times 10 to the 4 grams. So that's 3 sig figs. This is 4 sig figs, adding a 0, adding another 0, that would be 5 sig figs. Okay, so now in calculations, so this is going to sort of summarize and put into words some of the rules we were discussing earlier. The least certain measurement limits the number of significant figures in the answer. So if you're thinking, like imagine you're doing a problem, you have one really, really precise value and one really, really imprecise value. What's going to be that imprecise value that's going to limit the preciseness of your final result? For addition and subtraction, results are rounded to the inexact value's least significant placeholder. Okay, so let's think about that for a moment with an example. So let's imagine we have 255.5, and let's say we're doing subtraction. So we're going to subtract 125.45. And let's imagine this is, I don't know, some measurement of time. And then the idea being you're going to get to one placeholder and another placeholder. Maybe you're using two different devices to measure the time, hence why they have different different precisions. So if we do this into a calculator, 255.5 minus 125.45, I get on my calculator screen 130.05. What I have to do is look for the, what's it say? The inexact value's least significant placeholder. So the least significant placeholder is like the greatest quantity placeholder. So I'm looking for like the tenths placeholder is a greater quantity than the hundredths placeholder. So what we need to do is round this to the tenths place. So I'm going to go 130.1 seconds. And then for multiplication and division, results are rounded to the number of sig figs as the inexact value with the fewest significant figures. Okay, and so what we're being sort of careful here is to say like our measurements are inexact quantities. So I'm going to do two quick examples. Let's imagine we do something like 25.7 times 5.4. So in this example here, I'm going to do that in the calculator. So arithmetic is clear. That works out to be 138.78. And that this is only going to be good to 2 sig figs because the lesser precise value only had 2 significant figures. So we need to round to the same number of sig figs as the inexact values with the fewest significant figures, which is 2. So we would round this to be equal to 140, and let's put some unit here of meters and call that a square meter. If we want to be unambiguous, 1.4 times 10 to the 2 square meters. Okay, and multi-step problems, we're going to do some examples of these as we go, but we want to try to round just once at the very end of the problem, but we're going to apply the rules of significant figures as we do the different mathematical steps. So I think some examples will help us understand those nuances. One other example I wanted to give real quick. Imagine we're doing 1/2 mv squared, and we have just some generic mass. Let's say you have a mass of 125 grams, and then let's call that kilograms, just so we stay in the SI unit. So let's say 125 kilogram object is going 14.5 meters per second. So we have to square this. Okay, so if we're doing this particular problem here, one thing I want to note you to is the 1/2 is not an inexact quantity. That's just like in the equation. So that's an exact quantity. That's not an inexact quantity. The inexact quantities are the values that we have represented as measurements. So they're the measured quantities in the calculation. So I do 125 times 14.5 quantity squared, the 14.5 squared, and then we multiply that by a half, and that gives me 13,140, but this is only going to be good 13,100 to 3 significant figures. And that would be joules, because a kilogram meters squared per second squared is the SI unit of energy of the joule. So we got to be careful that we're only looking at the actual inexact quantities in the problem and not maybe conversion factors or other more precise values that may be either exact quantities or just pieces of an equation that are not inexact quantities. Okay, so we have some pause and predict problems, so give those a try, and we'll go over those in a moment. Okay, so let's review these problems. We have 5.25 grams plus 95.50, so we carry out that addition. We're not changing the arithmetic, it's just figuring out where to round. 5.25 plus 95.50. That in our calculator says 100.75, that'd be grams. And so we're good all the way out to the fives placeholder because we got hundredths place plus hundredths place, so we need to end the result in that same placeholder relative to the decimal. So the second place over from the decimal is where our answer is good to. Turns out it has 5 sig figs. Now when we multiply, we count sig figs. We go 1, 2, 3 sig figs. So we're going to round this result here to 3 significant figures. So 125 times 125 says 15625 on my calculator. I'm going to round that to 1.56 times 10 to the 4 meters squared to have a total of 3 significant figures. Division works out the same way. If I do this in a calculator, this obviously will just say 125 divided by 125. That's easy, it just says 1. But we have 3 sig figs divided by 3 sig figs. So this is actually 1.00 grams per milliliter. So if you know an object weighs 125 grams and it occupies 125 milliliters, then you can be confident the density of that object is 1.00 grams per milliliter. And that's different than saying 1.0 or 1 or 1.00000 grams per milliliter. Think about how precise you'd have to take your mass and volume measurements to determine this density here. You'd have to really precisely determine your mass and volume to get the level of precision to 1, 2, 3, 4, 5, 6, 7 placeholders. Okay, now a multi-step problem. Let's just think about our first step first, because that's the one we're carrying out before we do the division. So we do 121.55 subtract 101.67. Subtracting and adding have the same role. We're looking at the placeholder. Hundredths minus hundredths. We're going to round the result to the hundredths placeholder. That works out to be 19.88. So only good to the hundredths placeholder. So all the digits there are significant. So we have 4 sig figs in this result here after doing the subtraction. Now, if I had an extra digit, I would probably carry it along when I do the division. Not that it's going to make a huge difference, but we generally try to round just once. Not a problem here because we're keeping all 4. Divide by 14.55, and that works out to 1.366. And that's grams per milliliter for the units. And so all 4 digits are significant. We have 4 divided by 4 sig figs, so the result should have 4 significant figures. Okay, so now I have 5 minus 5 sig figs, but it's counting sig figs doesn't matter when you add and subtract. It's only where the placeholders happen to fall that really matters. Then when you multiply and divide, then you're counting sig figs and rounding the result to match the one with the fewest number of sig figs. So we use dimensional analysis to convert units. We also use it to solve a lot of problems in a class like this one. So we can apply conversion factors like 1 inch equals 2.54 centimeters. So we can do conversions using that as a conversion factor. And so we can set up ratios using conversion factors and solve a variety of problems using the technique of dimensional analysis. So let's look at some examples. So let's look at some examples. You might want to hit pause and give these a try. Okay, let's take a look at these. So convert centimeters to inches, so number of inches. when I use dimensional analysis, I like to start with what I'm looking for, begin with what I'm given, and then use our conversion factor, 2.54 centimeters per inch. You wouldn't have to know this. This would be provided. I mean, it's pretty obvious for most of us that this is the conversion factor, but we'd give you your non-standard conversion factors when you need them. So a really basic conversion. There is one little quick caveat here. So let's do 50 divided by 2.54. So the calculator says 19.685. And let me have you think for a minute, and there's some other digits too. Let me have you think for a minute. Do we round to 3 or 4 sig figs? You might say 3 sig figs if you're looking here saying, okay, that's 3 sig figs, this is 4. But remember, 2.54 centimeters, that's the exact number of centimeters in 1 inch. That's an exact conversion. It would be weird if a conversion factor was less precisely known than the quantity we've measured out that we're converting. We'd probably want to look up as accurate of a conversion factor as we can find, depending on the sort of preciseness of the value we're converting. Like if we're in a shipping business, we might want to be really precise and look up as precise of a conversion of, say, kilograms to pounds as we need, so we don't get, maybe charge more money than we should for whatever it is that we're doing business in. This problem here, we have 4 sig figs divided by basically an infinite number of significant figures. Remember when we started this whole discussion with inexact versus exact numbers? This is an exact number. This is an inexact number because this is representing some ordinary lab measurement of 50 centimeters. So that has 4 sig figs. The conversion factor has an infinite. Now let me say one other thing. If you really still believe it should be rounded to 3 sig figs, then you should probably round it to 1 sig fig, shouldn't you? Because 1 inch, that only has 1 sig fig. Like we'd agree that 1 inch is, the exact conversion, so it's the same thing with the 2.54. So we actually keep all 4 digits here, and we would round this to 19.69 inches for our correct answer to 4 sig figs. Okay, now let's do a volume conversion. So what is the volume in liters? So the number of liters would be equal to, starting with 2.50 kilograms of ethanol. We're given the density, but in grams per milliliter, so maybe we need to convert 1 kilogram, 1,000 grams. Now I expect you to know these prefixes on how to make the prefix conversions from giga all the way to pico. So we make the conversion over to grams, and then we can use the 0.7893 grams per ml, canceling out the grams, canceling out the kilograms, and then we want the volume in liters. 1,000 milliliters is a liter. So the milliliter cancels, and the 1,000 also cancels. So you can do 2.5 divided by 0.7893. You can also multiply by 1,000 and divide by it if you wish. But that works out to be 3.17 to 3 significant figures. So this is our inexact quantity. These are all either exact or more precisely known. This actually, I would say, is not an exact. That's just 4 sig figs on our density. So those are our 2 sort of inexact numbers in the problem. These conversions are exact, of course, exactly 1,000 grams in a kilogram. So this would be 3.17, whoops, I wrote that wrong, 3.17 grams per milliliter. Okay, so a final set of pause and complete video. So this one here, we're actually just trying to classify whether these items below are exact or inexact quantities. So give that a try. Okay, so if we count, we have 125 people in a room. We might have to do it 1, 2, or 3 times to really make sure we're actually counting correctly, but this is an exact quantity. So if you said there's exactly 125 people in the room, it's really not as if we're not sure if there's 124, 126. We can be exactly sure when there's 125 people in a room. 125.0 gram object, that's inexact. Anytime you see like some sort of value with a unit given and it's implying or it is some lab measurement, we're assuming that's one of these inexact quantities or a measured quantity. 16 ounces in 1 pound, that's an exact conversion. So that's an exact number. Exactly 1 pound contains exactly 16 ounces. And our final problem, if you want to hit pause, go ahead. But report the following calculation conversion to the proper number of sig figs. Convert 1750 liters. Now that's actually only 3 sig figs is what we'd assume that to be. We're going to convert that to cubic feet using these conversions here. So this involves a cubic conversion. Let's take a look at this one here. So start with what we're looking for. Start with what we're given. It's a pretty easy starting point. Now, where we might have to use our heads a little bit is we may have to remember a few conversion factors. Like a cubic centimeter is a milliliter. If we remember that, then we can go 1 liter, 1,000 milliliters, and then 1 milliliter is a cubic centimeter. You may not have to write this step out here, but that's our conversion over to cubic centimeters. Exactly 1 milliliter is exactly 1 cubic centimeter. And then from there, we can use our conversion that there's 2.54 centimeters in 1 inch. And then there's 12 inches in a foot. Now there's only one final consideration we need to make. That is, if we had a cubic inch, so we have a cube that's an inch by an inch by an inch, that would equal 2.54 centimeters along each of those cubes, the edge of the cube, so 2.54 centimeters cubed. So we have to cube this whole conversion. And so if I have, x over y quantity cubed, that would be equal to x cubed divided by y cubed. So, that simplifies down to 1 cubic inch is equal to 2.54 cubed centimeters cubed. Same thing, cubing the inches and feet on that conversion, we end up, doing 12 cubed, inches cubed equals 1 cubic foot. So 1 foot by 1 foot by 1 foot is 12 by 12 by 12 in terms of inches. Okay, so carrying out our arithmetic here, we do 1750 multiply by 1,000, and then we're going to divide by 2.54 caret 3, 2.54 raised to the 3, and then divide by 12 caret 3. That works out to 61.8. We should have 3 sig figs in our result. We have 3 sig figs here. Perfect. On the other conversions, so this ends up working out to 61.8 cubic feet. And one last thing we might do is kind of just a thought problem of 1750 liters, that's, cut that in half, number of 2 liters. This is a big volume. And a cubic foot is also a pretty big volume. And so you may think, is this like the right ballpark? If this said 6 million, we'd probably say, okay, that's probably a problem. If it said 0.1 cubic feet, we'd probably be like, oh, okay, the scale's off. So you may just check the magnitude of the result to decide if this happens to make sense. And I think it ties in. So let's double check our conversion here too. We go liter to liter, that cancels, milliliter cancels, cubic centimeters cancel. There's 2.54 centimeters, we cube that in an inch. And then our cubic inch cancels, and we're left with cubic feet. Okay, so it looks good. All right, so that concludes our Chapter 1 introduction video. Thanks for the attention. Look for the Chapter 2 video when we get closer to covering that in class.